and we just hope this will pass. But for our class, this actually is probably making no difference. I mean, in certain sense, I kind of feel after trying this out, maybe this is actually a very good way for us to do it. So now, are you seeing my screen now or not?
No, I do not see your screen.
Okay. So let's try this thing. So I'm going to share my screen. And let's see, I can pick something to share. How about now?
Yes, we can see it.
So you do see my screen?
Yes.
Okay, that's good. That's good. And how about this screen? Do you see? Do you see a PDF file or not?
I do not.
Okay, so how could I get another window to share? New share. Now I should be able to pick another. How about now?
Yes.
Yes.
Okay, can I, if I switch between this screen and another screen, do you see me switch between the screen?
Yes.
Yep.
Okay, so that's good. So apparently I can share individual screen and the multiple screens. So that's actually very good. Now I also want to let you know that the recording feature is on. So on my side, so this whole thing, they say going to be recorded. I'll see how this work out. And you know, if actually the recording makes sense or work well, I can just upload it. I don't know. It's actually good for future reference. But as part of privacy concern, I just want to let you know it is recorded. Okay, so you know it is recorded. Now, okay. Okay, so now how do I get the? I can move this to the other side. Not way to make this show small active speaker. Okay, I can make it smaller. Oh, okay, I can make this smaller. Why do you see this little where the mouse is, where it's now showing blind picture, or you only see the PDF?
I'm seeing the PDF.
Yeah, only the PDF.
So you don't see this. I have this on now you see my mouse, do you?
Yeah, we can see your mouse.
On top of my mouse, there is a little window which showing has a picture which showing whenever one of you guys talk, but that somehow you don't see that. You only see the PDF screen, right?
Yes.
Correct.
Yeah.
Okay. That's okay. Oh, why is that? It's okay. Let's get this span noise. Okay, so I think with this, it seems to be working out. How about we try? If you guys now, how do I? If one of you raise questions, I guess it's because we're a small group, you can just speak up. So that's not the issue. I think that. So, and I do want you guys to periodically ask questions or give me some feedback, so I know you are engaged. Because otherwise it's just monotone on my side, and then it's not like a classroom because I cannot really know how on your side it's going. So periodically, don't be silent for too long. Okay. Now you said your internet.
Okay, I'll try.
Yeah.
Sounds good.
Okay, any of you guys questions now?
No.
Oh yeah, I have
what
one. Like, what's your plan for the final exam? Like, how are we gonna do that?
For final exam, it'll be very much like a midterm exam. So plan is very similar, but now obviously you will not be in the lecture room, but it will be somewhat the same format. I will have a couple problems which I will require you to finish in 2 hours or so. Okay. Basically, once it's like only that's presumably, and we probably would try to do this since early if we instead had to wait. I mean, we're a small group enough. If there's a alternate time of final exam time you guys prefer, I can schedule differently from official final exam time. But in terms of contents, the format, it will be similar. It'll be, so I hope probably one or two problems which you should able to do it on paper, and if you're home, it will open book also again. So it's not a big closed book, so you don't have to memorize anything. And then I say I give you some limit amount of time, you write it out, and then you can take a picture and send in. So I think, and then there'll be one or two problems which you ask you to do numerically, graphically on computer. So you submit as you did with the midterm. I mean, you guys all did very well in the midterm. So I don't expect there to be you guys have big issue. Yes.
Okay.
Other questions?
Nope.
Okay. How about your other classes? You've been contacted with by your professor about your other classes?
Yep.
Yeah.
It seems like everyone's trying to just like get this all figured out.
Yes. I think it's really for larger introductory class, and particularly the one with the lab. I don't know how they're going to handle it. That would be it's a difficult one. Now I'm going to start this in by moving back to. Okay, the other thing is you notice I have this PDF file, which is the first edition of the Stronggate's book, and I assume some of you probably have it, and if you don't, and you can either use your current book, or if you don't have anything to access, you can let me know. I don't have the PDF file for second edition, but most of the contents are almost exact the same. For the homework, as for the homework assignment, now I was specify in which edition the corresponding problem, but I think mostly are same. And so this is for the convenience, since the content is essentially saying I'm going to use this as a basic of lecture, because lecture in essence is basically a condensation of my version of reading the book, plus some computation numerical, which I will show on the Jupyter lab. I haven't got to chapter 9 yet. Where it is chapter 9? Seems to be take forever. Step now. I should move this a little bit. Okay. This is chapter. No, past this. So what I'm going to do is essentially because I just want to try these things out, and as I said, it's recorded. I'm going to repeat the lecture on the mapping. Okay, and so first part of this will be essentially, no, I just had difficulty finding the beginning of chapter. Oh, no, it's not chapter 9. I want chapter 10. Okay. Here it is. So it's a one-dimensional map that we had one lecture before the spring break, but I think it's just good for us to restart this. So I'm going to repeating some of the stuff we talk about it. So again, the reason we start the map is three, namely, you know, you can see these highlights things I did right here.
Mm-hmm.
Okay.
Yeah.
So it's a tool for analyzing differential equation, because we convert differential equations to different equations, then essentially it becomes a map. Then of course there are phenomena which can be modeled by discrete map, and so there are phenomena. And finally, which is really the main interest for us, is this is a much simpler model to show the complexity and the various aspects of chaos, which we touch upon in last chapter when we talk about the Lorentz equation. So where it's a three-dimensional things, and this chaotic behavior or strange attractor is a object which is, you know, it's hard to analyze because three-dimensional. So that's the reason, three reasons we started as map. And so mapping again is basically say, if giving a state of the dynamic system, current state, and it's predict the state in the next discrete time or next iteration or whatever you want to think about it. And then so basically it kind of like in mathematics sometimes it could kind of Markovian process. Immediately the next time is only depend on explicitly on current time. Of course, one can think about more complicated map, which is a next step depend on the previous map, previous step, or two step back, for example, and so on and so forth. And then we study in this chapter only one-dimensional map, namely dynamic variable is only one dimension. But you can surely think about this all as a vector, like x0, x1, x0. And so therefore, this can be a full n-dimensional map. It doesn't have to be one dimension. So many of the things we talk about here actually will apply. Okay, so that's the general about the map. Now the first point about the map, it's just like a dynamic system is a fixed point. So imagine we have a map which is formally defined as xn equal to xn plus 1 equal to f xn. So f is a function which defines the map. So given the state at xn, we can find what xn plus 1. Now a fixed point is to say the next state, the state in the next iteration is the same as the state in the previous iteration. So therefore fx star, which is our usual notation, will be equal to x star. So let's define the fixed point, right? So it's just the same thing as what we have talked about so far in the earlier chapter. That's the same. Is in the previous case, we do fx star equal to 0, namely the things that's not changed. But here, since it's discrete, that's no longer a time variable. So therefore, the fixed point is defined fx star equal to x star. Then to analyze the stability around the fixed point, so we imagine, let's say, at the nth step or nth iteration, that the state is slightly deviate from the fixed point. So xn equal to x star plus eta n. So eta n is supposed to be a small quantity, which is a small deviation from the fixed point. And then we want to know how it propagate this deviation. So we plug this into a function fx, then we get xn plus 1. And since eta is a small quantity, we do Taylor expansion. So the Taylor expansion saying fxn star plus eta n equal to fx star, and then first derivative evaluate x star and times eta n, and then higher order term. Since eta n is a small quantity and higher order term, we can neglect it. And since x star is a fixed point, so fx star equal to x star. So therefore, that's x star and x star on both sides cancel out. And what do we end up with? Eta n plus 1 equal to f prime x star times eta n. We don't need to worry about higher order term. So therefore, the stability of the fixed point will depend on this derivative of function evaluate at the fixed point. This quantity f prime x star is generally called multiplier. So therefore, if this multiplier is less than 1, therefore the deviation from the fixed point getting smaller and smaller, getting smaller, smaller. Right. So therefore, the fixed point will be a linearly stable. What you call. So if lambda, which is derivative of the f star, f evaluate the fixed point, the less than 1, then it's linear stable. And of course, conversely, if this absolute magnitude is greater than 1, then the fixed point is unstable. So so that, and then in the special case where equal to 1, which is called marginal case. So marginal. So generally, if we have parameter change in the system the fixed point may change from stable to unstable going through the marginal point, goes through the marginal point. So let's look at the trivial example. Like x, the function is just x squared. So xn plus 1 equal to x squared. The fixed point, namely, if you plug this in, then obviously there's two fixed points. Namely, x equal to 0 or x star equal to 1. So there's a two fixed point. And to evaluate its stability, then we take this derivative of the function and then evaluate at x star. So for fixed point x star equal to 0, the derivative is equal to 0. Therefore, that is a stable fixed point. And for the other one, x star equal to 1, this derivative or multiplier will evaluate to be 2. So therefore, this one is unstable. It's unstable. Right. So it's a kind of trivial example. Now, this stability also can be graphically analyzed in terms of cobweb diagram construction, which we did in the classroom on the board. And here just repeat what that's in. So generally, genetically, this cobweb construction is following. We have this function, a general function fxn, f as function of x. This axis is x, and then this x is also x. We draw a. Why my phone keep running? Something. Let me see whether it's a way for me to silence. I should silence this since some kind of text gang keep popping up. So let's say I choose x0, and then I evaluate the function fxn. That give you x1, and then you do horizontally. It intersects with this line, which is xn plus 1 equal to xn. Then I get a new, get x1, because it's my x1, and then I evaluate the function at the function, and then go horizontally and keep go on. So that's how we get propagate from x0 to x1, x2, and so on and so forth. So that's a cobweb construction. Now let's look at the example. Let's say now a new map, which is a sine x. So xn plus 1 equal to sine x. If we do analytical analysis, there is a one fixed point, which is when x star equal to 0. So x star equal to 0, we can evaluate f prime. F prime, if you evaluate at 0, give you 1. So this is the case, the marginal case. So a marginal case, it can be turned to be, it can be stable or unstable. So it's not good enough. Actually, you need to go to a higher order term derivative. But if you look at the, this cobweb construction, then actually you can clearly see it's a stable because here's a cobweb construction. So this line is y equal to x or xn plus 1 equal to x, and this solid curve is a sine x. So if you pick an arbitrary value of x, you evaluate the function and you horizontally propagate into this diagonal line. You can see it doesn't matter where you start with. This is repeatedly step into it, and eventually it just very slowly converge to x equal to 0. So x0 in fact is a stable fixed point. So using the cobweb construction. Now you notice that that the slope, if you evaluate the slope at x equal to 0, is exactly 1. But once you deviate a little bit away from x equals 0, this slope actually is slightly smaller than 1. This actually analytically you can do it by doing Taylor expansion up to next order. Then you can show the slope actually is a little bit less than 1 once you moving away from x equal to. So that's why analytically you also can show this is stable. This fixed point is a stable. The fixed point here is a stable. Yeah, okay, I can get highlight there. Okay. So this is in the case x, the map is a sine function. Here's another example where the map is a cosine function. So if it's a cosine function, you can go the same thing. The fixed point is to say x equal to cosine x, x equal to cosine x. You can solve it numerically, and that gives you one fixed point. And if you evaluate the derivative of this thing, it becomes sine x, and sine x, of course, is always less equal than 1 as long as it's not a pi over 2. So clearly it's not pi over 2. Then this will be turned out to be less than 1. So you can see that fixed point is also stable. It's also stable. But in fact, you can show. So here's a cobweb construction. So the fixed point is where the curve, the function, intersect with this diagonal line. So here is the fixed point. Here's a fixed point, and you can see that no matter where you started with, this is using the cobweb construction. You will actually, this is actually pretty quickly converge to this fixed point. So if you start, for example, here, you can do the same thing. You evaluate to this point, and then you jump to here. Then you jump to here, and then you go on. You evaluate even you evaluate at this point, for example, you jump down here. So say you jump down here, and then you go all the way around here, and then you go up, and then go on. Well, my cursor is huge. I don't know whether there's a way to change this cursor to be smaller, but you get the point that this will be stable. Okay, so it's not intuitive and clear where to analyze the stability of the map. Okay, now because the main interest for studying this chapter is the logistic map, which we went through a little bit. So this is a logistic map. It's just like a logistic equation. That's one variable r. So r is a parameter, and if we solve for fixed point, namely x equal to rx 1 minus x, you find there are two fixed points. One is a trivial fixed point where the x equal to 0. Another is x equal to 1 over minus 1r, which I will come back in a minute. This logistic map is what was first proposed in 1976, and So it's not long, but it get a lot of fascinating behavior. So here I'm showing, and the interesting things is all between R between 0 and 4. And if you ask it between 0 and 4, you can show if you plot this function out, this is a quadratic function, and the maximum of this quadratic function is at exactly x equal to half, and the maximum value is r equal to r over 4. So we will just plot this window to analyze this. So the first case is to find a fixed point. So you know there is one fixed point is a 0, and you can calculate is a derivative. So if you calculate derivative of the function, so if derivative of this will be r minus 2rxn, and if you evaluate that at the fixed point x equals 0, so therefore the derivative at x equals 0 is equal to r. So when r is less than 0, 1 is stable. When r is greater than 1, it's unstable. Right. So this fixed point, okay. I don't know how I can highlight this. No, this fixed point is stable when r is less than 1. So for small growth rate r less than 1, the population always go to 0, because xn x equal to 0 is a stable fixed point. And basically r is the slope of this quadratic curve here. So when r is less than 1, the slope here is less than 1, is basically just a quadratic equation, and you can do covert construction, show that everything is just go to in fact, this is only fixed point, because if r is less than 1, this quadratic curve is below y equal to x. So the only intersection at this point, so that's only one fixed point, and it's globally stable, global stable. So here is the case where r equal to 2 point, and in fact, you can show now if r is greater than 1, there's another fixed point. So I'm going to now move, switch to my. Now, do you see my Jupyter Note page?
Yes.
Okay. So let's say let's try say r equal to 0.5, and I'm gonna run this since. So you can see this is r equal to 5, and so I have this line. This line is y equal to x. Okay, so this line is y. You can notice I have different scale on x and the y axis. So if I start here, the covert construction will just go down. So that is a stable fixed point, and this is the only fixed point. And if you look at this x as function, xn as function of n, you notice it just go down and quickly go to 0. So nothing interesting. Now, if I get to close to 1, this now become a very slow process, because this slope now is very close to 1. So this take a long time to get here. So you can see the convergence to the fixed point now is slower. I only plot the last 50 point. I think I did I did the 100 point iteration. Okay. Now, actually, let me do 300 here. So I do 300 iteration. Now let's say just go through a little bit about 1. So let's say 1.05. So this is the case where well, I don't know, you cannot see that here. There is starting, there's another fixed point here now. You find out that the origin here is no longer stable, and in fact I start this point, and it's actually, I need to zoom in to see this thing, but you can see this thing gradually move to this point, and you don't quite see yet, so I don't have enough iteration. So maybe if I make this a little bit bigger, this will be easier to see. So if now I put I equal to 1.15, now you can kind of see there is a fixed point, and the last 50 iteration of after 300 iteration is essentially give you one constant value. So the fixed point is 0.13 something. So right here. And this behavior will be similar if you keep increasing R. So it's 1, for example, here's a 2. And so now you can see more clearly. So the covariant construction, you can see that is I start from this point, boom, 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 to here, and then it's basically converge to fixed point. So very quickly. So the last 50 point is just that particular fixed point. So all this is the behavior you can see that is same until you're reaching 3. So let's say if I close the 3, and the second fixed point is still stable, but now it takes longer time to converge to this thing. So you can see this is now the last 50 iteration of the 300 iteration, and it's still not quite convergent yet. So you can see but you can see it's eventually converged to that fixed point, which is at this place. At this place. Okay. Now the question is what happens if we go beyond R equal to 3. So let's say if we do like 3.1, or let's do 3.2. So 3.2, now you can see I start from here, and after a certain number of things, it's basically trapped into this loop, this big loop. And if I plot xn as function n, you can see it just jumping back and forth between larger value and a small value. So this one is a larger value, this point, and this point is smaller value. So it's basically jumping between this x value and well, this is smaller value. I'm sorry, this is smaller x1, this is larger xn. So jumping between this point and the left point. So you can see it's just jumping back and forwards. So if you add a smaller xn, you evaluate xn plus 1 will be larger point, and if you had a larger point, you evaluate the function, you get to the smaller point. So, and this is the behavior is what we call period doubling, and we're going to show a little bit later to see that this period doubling actually happened at exactly R equal to 3. But this is numerically how it is you can see this just oscillating between the 2 points. And so and then as you keep going, go back to this. So period doubling happens at R equal to 3. So this is just what they did R equal to this 2.8, and then 3.3 we did 3.2. Basically you get this oscillation between the two possible value. Now what happens if you go beyond certain value? So here I say 3.5. So let's try 3.5. So 3.5. So now you notice the 3.5. There are 4 possible values. 1, 2, 3, 4, and then it repeats itself. 1, 2, 3, 4. And if you look at the covariant construction, there's 2 loops. Basically 1, and then 2, and then 3, and then 4, and then it repeats itself. So it's like this. Right, so it's like 2 windows shifting to each other, by a little bit. So you have 1 value, 2 values, 3 value, and 4 value. So 1, 2, 3, 4 value. So somewhere there between 3 and 3.5 is the period get double again. So somewhere between 3 and 3.5 period double again. So in fact, say the population approach cycle that now repeat every 4 generations, and this is what it could double. So somewhere between 3 and 3.5 is doubling. So in fact, you can show this behavior keep doubling as increasing further value. So at r equal to 3, we get the first period doubling. So period 2 is born. And in fact, at r equal to 3.449 is doubling. So now become period 4. And at r 3.544 is doubling again. And notice the difference between these two successive doubling value getting smaller, smaller. In fact, if you take a ratio of the successive period doubling, so this is a ratio, let's say, 1 period doubling to the next period doubling. So this is the next period doubling, the difference between these two R value period doubling. You take this ratio is approaching a constant value of 4.66. That means the interval between these two values getting smaller, smaller by a factor of 4.6. So therefore, it's geometrically converged to this R infinity value, 3.569946. At this point, the period becomes infinity. And then when you go beyond this point, then you get something chaotic behavior. So this behavior, as we change R from this value all the way and the period, so this route, this particular way we get to chaotic behavior, we call period doubling route to chaotic behavior. So now you might think that if you go beyond this value, everything is chaotic, which is not quite true. Let's go back to my simulation. So here 3.5 is doubling. So what is the value? So the value is say 3.5699. So let's try 3.56. What is 3.56, for example? In this case, it's still many period. So you can see it's still, I don't know, this is probably, it's a 1 window, 2 windows, 3 window. This is probably periodic 8 or 16. Now let's do 6, 9, 1, 3.5. Is 5669 or 569? I think it's 5669, right?
For what?
What is the infinity? Where I get to?
It's 569.
569, not 669.
No, yeah, it's 5699.
Oh, 5699. Okay, so 5699. Still running.
It's not. Scroll back up.
So why it's not running? Because
no, it's up. Go up.
Oh, it's still up. Okay. Okay. So this has a many period. I don't know. There's a couple window here, a couple window there, and this is still periodic behavior. Now let's go beyond this thing. So once you go beyond this thing, so let's say 5, 7, and that is in a chaotic regime, and let's see. Wait a second. It looks like still in the periodic behavior. Maybe I didn't run long enough or something. 5, 6, 5, 6. So let's say your internet connection is unstable. Let's do 5.8, for example. No, get the wrong one. Yeah, I think I will need to run this to longer period of time. Let's see what the book, what the value they choose. Oh, 3.9. Okay, let's run 3.9. 3.9 case. 3.9. And maybe let's just run 500 point iteration. Okay, so this is now, you can see we are in the chaotic regime, so it's never repeat itself. But nonetheless, it does not continually occupy this whole line. It's actually a discrete set of points. It's an infinite set of points with a measure 0, but it's covered all this region. But has a measure 0. Namely, it has, if you add all those points together, it has 0 length. But even though there's an infinite point here, you can think about all the rational number, for example, is one example. All the rational number is occupied between 0 and 1, but they are only an infinitesimal small set of a continuous number, for example. So that's what it means. It's infinite set, but has a 0 measure. And here's the last 50 point. You can see it doesn't repeat itself. It doesn't repeat itself. So you might think this behavior just continues. So for all our value. So here's the corresponding covert structure. So I think my figure actually look better than this. I want more. I like 500 points. So this is so the question is to say you might guess that the system would become more and more chaotic as R increase, but in fact the dynamics are more subtle. And to see this subtlety, what we needed is construct this so-called orbit diagram, which is like a bifurcation diagram. And here's I think I showed this since this is the layout version. I showed this since in a lecture, and in fact I do have this in the Jupyter lab. So but I think this is a good point to stop for today. It's good enough. I think we'll pick up this back again. Would Thursdays okay for you guys?
Yep.
Okay, if it's okay, we'll pick up Thursday at exactly the same time. And now, meanwhile, if any of you has a individual or private question, okay, you're welcome to ask questions during lecture. But if you have individual private questions, you can always feel free to just shoot me email or something, okay? And that's good. And if those in campus, if you are running into any difficulty, you need to help beyond the class work. Just let me know, and I'm in charge here, so I'm more happy to provide any help I can do. All right?
Yes.
Okay, and I hope you all keep safe, and well, to a certain degree, enjoy this time at home.
Well, thank you.
Yes.
Okay, with that, adieu, and I'll see you on Thursday.
Okay. All right.
Bye.
Bye.